Stars are born, grow and die of old age, just like living things. Some stars end their lives with a bang, the loudest in the universe, and for a fleeting instant they may shine with the brightness of 1 billion suns. Over the past 5 years, the European Space Agency's Integral Gamma Ray mission, in cooperation with Russia and the United States, has provided high-resolution imagery and spectroscopy, locating high-energy sources, identifying their constituents and cataclysmic behaviors, and mapping the greater part of the sky.
Integral has observed more than 80% of the sky because it has this relatively wide field of view. So anytime we look at one field, we see a quite large field of sky around it. And doing that, we find new sources. 120 in the first year, more than 100 in the next year. And now it's about 500. Most of them are new sources. Typically, the systems will have like a giant star and this exotic compact object, a black hole or the neutron star at the side of it. And then we still have quite a bunch, a quarter about, which we don't know what they are.
Probing the most distant regions of the universe to the closest stars of our galaxy, the results of the mission are impressive. Looking beyond our galaxy, for example, science teams have located more than 100 supermassive black holes, 1 million times the mass of the Sun, and which are now believed to be present in space on a much wider scale. Another recently identified source, a quasar, is the farthest object so far detected by Integral, a gamma-ray lighthouse shining from the very edge of the universe. In our galaxy, Integral has detected by chance a rare kind of transient gamma-ray source. Examination of the unusually short rise and decline in its brightness suggests that the eruption came from a binary star system in which a sun-like star is being ripped to pieces by a nearby black hole. Investigation of high-energy bursts sometimes reveal objects like one very special neutron star whose behavior stretches our comprehension to the limit.
A neutron star is the compact core of a dying star, which has collapsed on itself. You remain with more than the mass of the Sun, concentrated incredibly dense, denser actually than the core of an atom. In this specific case, the detection by Integral and the bursts we found led to the measure of the period in it. This little piece of star spins more than 1,100 times a second, more than twice as fast as any previous source.
Integral has discovered a new class of celestial objects emitting X-rays, unidentified in previous observations, called now superfast X-ray transients, and probably widespread throughout the galaxy.
We have one supermassive star, typically a big blue star, much more massive than our Sun, and again a compact object, a black hole or a neutron star. The special thing about these systems is that they flare up just in minutes to really bright sources, and then again after a short brightness, after a few hours, they die away again. We are used to sources which get bright, but we are used to sources which get bright and stay on for days, weeks, even months. And so one reason we found, which these ones haven't been detected before, is because they are so brief.
Very active regions full of energetic objects can calm down. Integral has caught such a rare moment of quiet at the center of our galaxy, thought to be the location of a gigantic black hole called Sagittarius A star. As the observatory watched, the high-energy rays from about 10 variable sources all faded temporarily. Also in the galactic center, Integral has made a key discovery concerning antimatter and its annihilation.
We see radiation coming from the center of a galaxy, and we see a lot of radiation. And when we study this radiation, the only explanation is that we have normal matter, electrons, like we know, and the antimatter exterminating each other in a short flash of light at a very specific energy. And that is why we can observe it and say this must be antimatter. And the mind-boggling thing about it is that we have here 15 billion tons of matter per second, which must be created and destroyed in such a way. And currently there is no explanation of how exactly this works.
The interiors of stars are nuclear processing plants whose contents are spewed across space when they die. Integral has opened up a whole new field of investigation by providing definitive proof of the existence of a radioactive isotope, iron-60, in our galaxy.
This is another isotope than our usual workhorse, aluminium-26, which has, for example, been used to show that we will have a supernova every 50 years in the galaxy. But now with Iron 60, we have a very different isotope. It is produced much deeper within the stars and much later in their lifetime. So this gives people who are studying stars, who are studying supernova explosions, a completely different yardstick on what to test their predictions.
For each answer, then, given by the Space Observatory, like a magician, it is prompting even more questions.
One exciting moment in the life of a scientist is you see something and it doesn't match what you expect. You have an expectation, okay, so, and then suddenly, I don't understand this. That's the moment when it gets exciting.
Integral's Gamma Ray mission was originally to last just 2 years. With the achievements so far, no surprise then that it has been extended to 2010.